In this lecture, we're going to be looking at some of the rules for complex and rational zeros of polynomials. Let's start with the rule for complex zeros. If a polynomial f of x has real coefficients and a plus bi with b non-zero is a complex zero of f of x, then a minus bi is also a zero of f of x. Basically, this says that if a polynomial has real number coefficients, then the complex zeros come in conjugate pairs. Here's an example of where we could use this. This example says, find a polynomial f of degree 3 with real coefficients and leading coefficient 1 such that 5 and 4i are zeros of f. Let's start to construct our function f of x. The leading coefficient is 1, so we don't have to write in a placeholding coefficient a and solve for it later. We know that it's a 1. If 5 is a 0 of f of x, that means that x minus 5 must be a factor. And if 4i is a 0 of f of x, that means that x minus 4i must be a factor. Those can't be the only factors, though, because this would only be a polynomial of degree 2, so there must be a third zero somewhere. Can we just add any zero that we want to get up to degree 3, or can we just give one of these zeros a multiplicity of 2? We cannot because of this rule. If a polynomial has real coefficients, then the complex zeros come in conjugate pairs. We're told that this polynomial has to have real coefficients, and the only way that can happen is if the conjugate of 4i is a 0 as well. So the idea is that since 4i is a 0 of f, negative 4i must also be a 0 of f. It turns out that that's the only way that we could get real coefficients. Any zeros with imaginary parts have to have a conjugate to go along with it. So x plus 4i is also a factor of this polynomial. Typically, we're at least expected to multiply this out to prove that we have all real numbers. So minimally, we would have to multiply these together. That product is a difference of squares, and that's exactly why all the imaginary parts are going to disappear. X times x is x squared. The outer and inner terms are guaranteed to cancel because this is a difference of squares. And negative 4i times positive 4i is negative 16i squared. That would come out to positive 16. We could continue to multiply this out using the FOIL process and get x cubed minus 5x squared plus 16x minus 80. But the real point is to get to here and show that we've got all real coefficients. That rule is pretty straightforward. Sometimes this multiplication can be a little bit arduous, but it's not difficult. You just have to be careful. I want to focus more on this rule for rational zeros. When I read the rational zeros theorem, it's going to sound complicated, but it's really not that bad. Here's the rule. If the polynomial f of x equals a sub n x to the n plus a bunch of other terms all the way down to a sub 0 has integer coefficients, and if c over d is a rational zero of f of x such that c and d have no common prime factor, then c is a factor of a sub 0 and d is a factor of a sub n. The idea behind the rule gets masked behind all of this nerd talk. Suppose you've got a polynomial where all of the coefficients are integers, so you don't have any fractions, you don't have any square roots, you certainly don't have any imaginary numbers. They're all just integer coefficients. The only candidate fractional zeros have numerators that divide into the last term and denominators that divide into the coefficient of the first term, what we call the leading coefficient. Those are the only possible fractional zeros, and that includes fractions with denominator 1. So that also covers all the possible integer zeros. I could try to explain what this says all day, but it's really not going to make sense until we do an example. So let me show you an example here. This says, is x equals 1/2 a 0 of the function 9x cubed minus 13x squared minus 50x plus 24? This is a polynomial with integer coefficients. Notice that all of the coefficients are integers. The question is 1/2 a 0 of this? Now there's one straightforward way to do that, and that's to plug in 1/2. I understand that. But I want to show you how we can answer this question using the rational zeros theorem. What we're going to do is make a list of all possible rational zeros and see if 1/2 is in that list. Now how can we list all of the possible rational zeros? This rule says the only possible rational zeros are fractions in lowest terms where the numerator divides into the constant term and the denominator divides into the coefficient of the leading term, what we call the leading coefficient. So I'm going to make two lists. I'm going to make a list of factors of the constant term, which is 24, and I'm going to make a list of the factors of the leading coefficient, factors of 9. The factors of 24 are 1, 2, 3, 4, 6, 8, 12, and 24. Those are all of the numbers that divide evenly into 24. The factors of 9 are 1, 3, and 9. The possible rational zeros are all of the fractions that we can make positive or negative using the numbers in the first list for our numerator. The numerator has to divide into the constant term, and using denominators that come from the second list. The denominator has to divide into the leading coefficient. So this is a pretty big list. Let me start to make it. So it can be positive or negative. So we could have plus or minus 1 divided by 1, or we could have plus or minus 1 divided by 3, or we could have plus or minus 1 divided by 9. That's taking 1 and putting it over each of these. Or we could have plus or minus 2 divided by 1, plus or minus 2 divided by 3, plus or minus 2 divided by 9. Now I'm going to continue making the list here, but let's go back to the actual question. The question is x equals 1/2 a 0 of this polynomial? We can immediately see that it's not. There's no way to make a fraction equal to 1/2 by taking a number from the first list and putting it in the numerator, and taking a number from the second list and putting it in the denominator. We can already answer this question. The answer is no. But as an exercise, let's continue listing all of the possible rational zeros. We would start with 3 in the numerator. We would have 3 over 1. 3 over 3 doesn't need to be listed because that's not in lowest terms. Same with 3 over 9. That doesn't need to be listed. We would have plus or minus 4 over 1, plus or minus 4 over 3, plus or minus 4 over 9, plus or minus 6 over 1. We don't have to do 6 over 3 because that's not reduced. That's equal to 2, and we already have a fraction equal to 2. We don't have to do 6 over 9. That's equal to 2/3. We already have that in the list. We have to do 8 over 1. We have to do 8 over 3, and we have to do 8 over 9. 12 over 1. Not 12 over 3 or 12 over 9, those reduce. 24 over 1, not 24 over 3 or 24 over 9, those reduce. Now this is a really big list of possible rational zeros, but when you take it from the fact that we've gone down from infinitely many options to a finite number of options, this really isn't that bad. And if we combine this with the power of technology, then we can really get the ball rolling here. So I want to show you the motivation for me listing all of the possible rational zeros, other than to just demonstrate what the theorem says. Let's actually find the zeros of this polynomial, but we're going to do it with the aid of technology. So we're going to graph this function in the calculator. I'm going to go to my y equals screen, and I'm going to type the function in there. So 9x caret for an exponent cubed. If you have a newer operating system, you might actually get a superscript. You just type a 3 into it and then hit the right arrow. Minus 13x squared, there's a squaring key down the left side, minus 50x plus 24. And to make sure that we all get the same graph, we're going to zoom in on the standard window. We should only have to do this once. So I want you to press zoom and the 6 key to zoom to the standard window. That sets the x-axis from -10 to 10 and sets the y-axis from -10 to 10. Now, we get a pretty ridiculous looking graph, but we can see parts of it. Like I can see this part right here, and it looks like it goes somewhere around -2. I see this one here that comes at about 3. And then there's this one that looks like it's halfway between 0 and 1. And this is why I asked that question on the previous slide. Is that x equals 1/2? We know it's not x equals 1/2 because it's not in our list of possible rational zeros. 2 of these solutions are pretty easy to find. That looks like -2, and notice that -2 is in our list of possible rational zeros. It's right here. If you push your trace key and then type the number you want to go to, we think -2 is this spot right here. Hit enter, and it will tell you -2 is one of the zeros. There's another one that looks pretty easy to see, and it's over here. It's at 3. Is 3 in our list of possible rational zeros? If it's not one of the possible ones, I'm not even going to bother guessing it. But yeah, 3 is in our list. Positive 3 divided by 1 is right here. So that's a reasonable guess. We've already hit trace once, so I don't need to hit it again. I can just type 3 and hit enter. And yeah, that's a 0 as well. Okay, sweet. We've got 2 of them. And then there's this third one that's somewhere between 0 and 1. And here's where the theorem comes in handy. I'm going to look at the fractions that we have between 0 and 1. There's 1/3, that's a reasonable guess. 1/9, it doesn't look like 1/9. It looks like it's further away from the axis than that. But it could be 1/3. What other reasonable guesses do we have? We have 2/9. We have 4/9. It doesn't look like 8/9. 8/9 is almost 1. Those are the only fractions that are worth guessing. Something between 0 and 1. Let's start with 2/9. If we guess 2/9, and I can type 2/9 by doing 2 divided by 9. That didn't give us 0. That's not the right guess. We can't even see the point because its y-coordinate is bigger than 10. It's somewhere up here. 2/9 appears to be too small. It looks like the function's decreasing on this interval. And so I'm going to have to pick something bigger than 2/9. What other fractions did we have? We had 4/9. Let's see if 4/9 works. 4 divided by 9. Enter. Oh, that's it. The other 0 was 4/9. By having the list of possible rational zeros, we were able to quickly guess what that fraction was. Let's do another example of this, and we'll start with the calculator to see if we can get rolling, and then we'll go from there. This one says, find all solutions of the equation 6x cubed plus 7x squared minus 18x plus 5 equals 0. Okay, I'm going to clear out this old function, go to my y equals screen, hit clear, and we're going to type in this function. I'm going to start with the graph, and if I need the rational zeros theorem, then I'll invoke it. So let's look at what the graph looks like. We don't need to zoom again, we're already zoomed to the standard window. So I get an answer here. It looks like it's somewhere between -2 and -3. I get an answer here. It looks like that might be 1. And I get an answer here that looks like it's 2, but we know that 2 can't be a solution because 2 doesn't divide into 5. It's hard to tell what those answers are. We can be hopeful that 1 is a solution. Let's check. If we push trace 1 and enter, hey, that's one of the solutions. X equals 1 is a solution. At this point, we have two options. These other two zeros might be rational zeros. So if we made a list of all of the possible rational zeros, we might be able to guess what those are. Alternatively, we could start dividing to get this thing factored and see if we can get their zeros that way. I'm going to show you both methods. Let's start with the rational zeros theorem since that's what I'm trying to show you how to do. So, what are the possible rational zeros? Well, any zero of this polynomial has to have a numerator that's a factor of 5, the constant term. And the only factors of 5 are 1 and 5. The denominator has to be a factor of the leading coefficient, which is 6. 6 only has 4 factors, 1, 2, 3, and 6. This list is going to be a lot smaller than that ridiculous list in our first example. So we can do plus or minus 1 over 1, plus or minus 1 over 2, plus or minus 1 over 3, plus or minus 1 over 6. Those are all of the possibilities with the numerator of 1. Or we could do plus or minus 5 over 1, plus or minus 5 over 2, plus or minus 5 over 3, and plus or minus 5 over 6. Those are all of the possible zeros with the numerator of 5. Now when you get experience with this, you might not list some of these. Like one of the possibilities I listed was plus or minus 5 over 1, but if you look at the graph, there's no way that 5 is a 0. The graph doesn't go anywhere near 5. I've got my eye on this one. This one looks like it's somewhere between -2 and -3. Do we have a number in here that's somewhere between -2 and -3? Yes. -5/2 is -2.5. That seems like the only reasonable candidate. If that's not a solution, then we're going to have to try something else. Let's check. I've already hit trace, so I can just type -5 divided by 2, cross my fingers and hope. Oh, good. That's right. -5/2 is a solution. I'm not sure why I was so formal here. Let me erase this. There's one more solution, and it's over here on the right, and it looks like it's between 0 and 1. Remember, this was x equals 1. So we're somewhere between 0 and 1. What fractions do we have between 0 and 1? Well, we've got these, 1/2, 1/3, and 1/6. And then we've got 5/6. It doesn't look like it's 5/6. 5/6 would be closer to 1. It looks like it's actually to the left of 1/2. My guess would be that it's positive 1/3. Let's see. I'm going to type 1 divided by 3. Oh, another lucky guess. Or maybe I'm the person who wrote the problem and I knew that the solution was 1/3. Whatever. I'm able to guess what those fractions are because I have a list of the possible rational zeros. That's one way to find these solutions with the help of technology. However, there is an alternative. Let me clear some of this. Starting with the solution x equals 1 that we could easily see in the graph, I can start to do division to break this thing down. I'm going to put 1 in the nook and divide this out. I'm guaranteed to get a remainder of 0 because I know 1 is a 0 of this function. So drop the 6 down. 7 plus 6 is 13. 1 times 13 is 13. Negative 18 plus 13 is negative 5. 1 times negative 5 is negative 5. Negative 5 plus 5 is 0, just like we expected. And so that tells us that we can actually factor the original polynomial to x minus 1 times 6x squared plus 13x minus 5. And now it turns out that we can factor this expression. 3x times 2x to get 6x squared. I need to put a 5 somewhere, and if I put a 5 over here, that'll give me 15x. That means I need to put a 1 here. Positive 13 in the middle, so this is plus and this is minus. And now I can get the solutions. This is x equals 1. This is x equals 1/3. This is x equals negative 5/2, which is exactly what we got by applying the rational zeros theorem. Let's do another example, and I want to focus on this process of breaking the function down using division. This example says, find all solutions of the equation x to the 4th minus 5x cubed plus 31x squared minus 125x plus 150 equals 0. We could make a list of all of the rational zeros. I want you to notice that they'll all be integers because the leading coefficient is 1. So the only possible rational zeros are numbers that divide into 150. You might just guess one of them and come up with it. But I'm not going to guess. I'm going to use the calculator to see if it will give me any information. I've pushed the y equals key. I'm going to clear out my old function. I'm going to type in the new one. I can just push the graph key because I'm already zoomed in. So I see two spots where the graph touches the axis, and if those are rational, then they have to be integers. So the only candidates here are positive 2 and positive 3. Notice that both positive 2 and positive 3 divide into 150. That's a good sign. Let's check. I'm going to hit trace. It looks like 2 is a solution. It is. It looks like 3 is a solution. It also is. So we know that x equals 2 and x equals 3 are solutions. But the graph doesn't show any other solutions. There are a few possibilities for why that might happen. One might be that the other solutions are way off the screen. Like remember, we've only got this stretch from negative 10 to 10, and our constant term is 150. So maybe one of the solutions is much bigger. That's one possibility. Another possibility is the multiplicity of one of these zeros is bigger than 1. It would have to be an odd multiplicity, so the multiplicity would have to be 3. That's a possibility. We would only find that out by factoring. The last possibility is that the other solutions are not real numbers. They fall into the set of complex numbers with non-zero imaginary parts, and the only way we're going to find those out is by factoring. So it looks like we're stuck factoring here. We're not going to be able to steal any more zeros from the calculator like we did in the previous examples. You can take either zero and divide it in first. I would start with the smaller number when your list is really long. So I'm going to put 2 into the nook. I'm going to write down the list of coefficients here. And I'm going to do synthetic division. The 1 drops down. 2 times 1 is 2. Negative 5 plus 2 is negative 3. 2 times negative 3 is negative 6. 31 plus negative 6 is 25. 2 times 25 is 50. Negative 125 plus 50 is negative 75. 2 times negative 75 is negative 150, excuse me. 150 plus negative 150 is 0. You should not be surprised that we got a remainder of 0 because we already knew that 2 is a 0 of this polynomial, that x equals 2 is a solution. Now that gives us a polynomial that we could break down, but we're going to take advantage of the fact that we know 3 is a 0 as well. I'm going to take that new list of coefficients, don't write down the remainder, and I'm going to do the synthetic division again with x minus 3, putting 3 in the nook. The 1 comes down, 3 times 1 is 3, negative 3 plus 3 is 0, 3 times 0 is 0, 25 plus 0 is 25, 3 times 25 is 75, and negative 75 plus 75 is 0. Again, that's not surprising. We knew that was going to happen. So what have we done at this point? We've taken this original function, x to the fourth minus 5x cubed plus 31x squared minus 125 plus 150, and shown that x minus 2 is a factor that comes from the first line. We've shown that x minus 3 is a factor that comes from the second line. And keeping in mind that this is x squared, this is x, and this is the constant term, the last factor is x squared plus 25. And now it becomes clear why we were only able to come up with those first two solutions. The last two solutions come from solving the equation x squared plus 25 equals 0, which is going to yield imaginary answers. If x squared plus 25 equals 0, then x squared equals negative 25. And so x equals plus or minus 5i, and those are the other two solutions. X equals 5i, x equals minus 5i. As an aside, notice that those two solutions came in a conjugate pair, just like they have to because all of our coefficients are real numbers. So we get 4 distinct solutions. 2 we stole from the calculator, and I'm encouraging you to do that. Any solutions that you can see in the calculator, you're absolutely allowed to steal. Those are easy ones to find. But we only found 2 zeros, and this is a 4th degree polynomial. It could have as many as 4 solutions to this equation. So we weren't sure if we weren't seeing the other zeros because they weren't on the screen, or because there were repeated factors, or because there were imaginary solutions. So we took it into our own hands. We did the factoring ourselves, and we said, okay, that's why we're not seeing the third solution. We have to solve x squared plus 25 equals 0, which yields imaginary solutions. Okay, let's put all of this together. We're going to find all of the solutions of the equation 3x cubed minus 2x squared minus 10x minus 16 equals 0. I want you to graph the function on the left side using your calculator and determine the 1 0 that you're able to see. You're only going to see 1 0 on your screen. I want you to figure out what exact fraction that is. Okay, here we go. I'm going to go to my calculator, clear out all of this other junk, and put our new function into y1. I'm going to graph this function on the standard window, and as I said, there's only one solution there. It kind of looks like it goes through positive 3, but I hope you can see it can't go through positive 3 because 3 doesn't divide into 16. So that isn't 3. You could have checked it. If you push trace and hit 3 and enter, you'll see that that's not a solution. It looks like it's some number between 2 and 3. The rational zeros theorem tells us that any 0 has to have a numerator, which is a factor of 16. The factors of 16 are 1, 2, 4, 8, and 16. And the denominator has to be a factor of 3. Well, the only factors of 3 are 1 and 3. Now, in previous examples, we made this ridiculous list of all of the possible rational zeros, but let's be a little more realistic here. We've already determined that the solution we're looking for is between 2 and 3. I want you to find all of the fractions you can create that are between 2 and 3, where the numerator comes from the first list and the denominator comes from the second list. This is the beautiful thing about this theorem. There's only one possible fraction. Our candidate is x equals 8/3. 8/3 is between 2 and 3. None of the other fractions are. So if it isn't 8/3, then we're stuck. Let's see. I've already hit trace, so I can just do 8 divided by 3, enter. Nice. 8/3 is the 0. But now what? What do we do? Well, we're stuck trying to divide this out. That's okay. Synthetic division with a fraction can be done. 3, -2, -10, and -16. I know this looks like it's going to be awful, but remember that the answer is going to come out to 0, so it's really not going to be that bad. Like when I drop down the 3 here, 8/3 times 3 is 8. And -2 plus 8 is 6. And I'll be able to get an integer again because 8/3 times 6, well, 3 goes into 6 2 times. 2 times 8 is 16. That comes out to 6. 8/3 times 6 is still 16, and of course I get a remainder of 0. So in a weird way, we've factored this to x minus 8/3 times 3x squared plus 6x plus 6. If you've seen this done before, you know we can factor a 3 out and distribute it through here so that we don't have a fraction. But our goal isn't to get this factored. Our goal is to find the solutions. So we already know the solution that comes from this one is 8/3. And now we just have to solve this equation. 3x squared plus 6x plus 6 equals 0. Dividing everything by 3, that's x squared plus 2x plus 2 equals 0. And now we can apply the quadratic formula. That doesn't factor, so we get -2 plus or minus the square root of 2 squared, which is 4, minus 4 times 1 times 2, that's minus 8, all divided by 2. That's -2 plus or minus the square root of -4 over 2. That's -2 plus or minus 2i divided by 2. That's -1 plus or minus I. And there are our last two solutions. X equals -1 plus I, and x equals -1 minus I. And notice that those two solutions came in a conjugate pair. If you get a solution with an imaginary part when all of your coefficients are real numbers, then there's a second solution with an imaginary part. It's just the conjugate of the first one. So in that example, we used both ideas. We went to the graph to steal a 0, but we didn't get lucky like in the previous example. The solution wasn't a whole number, it was some fraction. So we used the rational zeros theorem to guess what fraction it was, and we got lucky. There was only one reasonable guess, and it worked. You should know that there are some equations that don't have any rational solutions. I'll show you that in a second. But this one did. It was 8 divided by 3. We used that to break down the function into two factors, and then we just solved the equation when we set the second factor equal to 0. We saw why we were having trouble finding the other solutions with the calculator. Those other solutions were not real numbers, so you're not going to see them in the graph. Now I just mentioned that not all of these equations have rational solutions. I want to show you an example of that. This problem says, show that f of x equals 2x cubed minus 8x plus 3 has no rational root. Let's graph that left side in the calculator. Clear out my old function. 2x cubed minus 8x plus 3. When you graph this, you see that there are actually 3 solutions. It looks like there's a solution around -2, there's a solution between 0 and 1, and it's hard to tell where that last solution is, but it looks like it's just bigger than 3. This equation has 3 real solutions, but none of them are rational numbers. How do you prove that? Well, your first job would be to make a list of all of the possible rational zeros. That's your job. Will you list all of the possible rational zeros for me, please? Any rational zero will have a numerator which is a factor of 3, and will have a denominator which is a factor of 2. The factors of 3 are 1 and 3. The factors of 2 are 1 and 2. And so there's not a really long list here. There's plus or minus 1 divided by 1. There's plus or minus 1 divided by 2. There's plus or minus 3 divided by 1. And there's plus or minus 3 divided by 2. And using technology, one way to do this would be to put all 8 of those into the calculator. So for instance, I could hit trace and say, okay, is it at +1? Well, you can see it's not at +1. -1, I can see that one too. It's not -1. Like this one here, looks like it's at 3. That's a reasonable guess, but that's not right. This one here looks like it's at -2, but -2 is not even on our list, so we wouldn't check that. Right? So we could just plug all these in. Another option to see if these are rational zeros is to just plug each one into the function. So you can plug in 1, plug in -1, plug in 1/2, plug in -1/2. Instead of using the calculator, you could just plug them all in yourself. I did this the nerdiest way possible. Right? I got to keep my rep as King Dork here. So I used synthetic division with all of the possibilities. I started with the integer possibilities. +1, -1, +3, -3. I didn't get a remainder of 0 on any of those. Then I did the same thing with all of the fractions. and these got kind of messy quick. So we checked all 8 of the possibilities, none of them worked, so there's no rational root. Now I want to reiterate, that doesn't mean it doesn't have any roots at all. You can see it in the graph, there are 3 of them. They must just be weird roots of some type. In fact, there is a procedure for finding them. There's a formula similar to the quadratic formula for cubic function. I've seen it before, but I don't know it by heart or anything. It's not something that you really have to use very often, especially nowadays. But there is a formula that will find them. It's not something we need to know. We were basically charged with showing that there aren't any rational roots. We don't actually care what they are in this example. Okay, so we looked at 2 rules for zeros of polynomials. We said that the complex zeros come in conjugate pairs. We said the rational zeros have to follow this strict rule from the rational zeros theorem. I would encourage you to dig up more examples of this type where you're solving equations, and I want you to cheat with the calculator. Steal as many of the rational zeros as you can, using the list of possible rational zeros if you have to, like we did in this example. And then if there are more potential solutions, then use division to come up with the other factor and solve the equation. If you have any questions for me about how the rational zeros theorem works, or how we did any of the examples in this video, please reach out to me. You can catch me in an office hour, or you can shoot me an email.